Hey everyone. In the last lesson, we learned how to extract hidden structural information from a molecular formula using degrees of unsaturation. Now we're going to answer the next question. How do chemists actually draw and name those structures efficiently? This lesson will focus on three tools you will constantly use in organic chemistry and the U.S. National Chemistry Olympiad: bond line structures, structural isomerism, and alkane naming. Let's start with why bond line structures exist. If we really tried to draw every carbon and hydrogen explicitly in the way I'm trying to do right now. For example, this molecule is a simple molecule, just butane. But drawing this is honestly taking a while, and it is very unnecessary. Imagine a 108 carbon compound, and you have to draw every single carbon. That would be really, really bad, right? It would really suck for the chemist. So this is butane. Now, chemists use a shorthand called bond line notation, where each line represents a bond. Each vertex or line endpoint is a carbon atom. Hydrogens on carbons are implied, and they're not drawn out. Oops. For example, this is butane in bond line structure. Much simpler. So you might be wondering, how does that even resemble butane? Well, in bond line structure, the hydrogens are not drawn, but they are technically right here. They're implicitly there, but they're not explicitly there. But how do I know if there's two hydrogens or three there? Well, carbon always forms four bonds, and if the hydrogens aren't there, you can see that this carbon, which is right there, remember I said each vertex is a carbon, has two bonds. So if it has two bonds with other carbons, then that means the rest of its bonds have to be hydrogen, and this is a must in organic chemistry. You always assume that. So, for example, this carbon right here, since there's only one bond that means it has three hydrogens attached. Same goes for this carbon. Since it only has one bond, it must have three hydrogens. Let's try another molecule. Oops, that's not a really good cycloalkane, is it now? Let's do cyclohexane, for example. Let's do this carbon. If it has two bonds with two other carbons, then that means it must be bonded to two hydrogens implicitly. Now, what if I add a double bond right here? We haven't learned about alkenes much, but this will help with bond line structure. Well, you count the alkene as a bond itself. So there's 1, 2, 3 bonds that this way I have not defined the carbon. This carbon is bonded to 1, 2, 3 different carbons. As a result, it has one hydrogen attached to it. And I didn't explain that well. It's bonded to 2 different carbons, but it has 3 bonds in total because of the pi bond. So it only has one hydrogen attached to it. And remember unsaturation? That's what pi bonds and rings do. They basically take up a bond that could be used for hydrogen instead. And we can use unsaturation to give us hints on how to draw certain structures based off the amount of hydrogens there are compared to the relative number of carbons. So that's bond line structure. And so when you see a carbon with 2 bonds already drawn, you automatically know it has 2 hydrogens attached as a result. Just like the case is for this carbon, I mean. Another interesting molecule to draw would be this molecule right here, which has a triple bond actually. this would be carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. So this would be pentyne. You have not learned the "-ine" prefix, but that is when there's one or more triple bonds. This carbon right here has 1, 2, 3 bonds to carbon 2, which is this carbon. As a result, since it has 3 bonds to carbon 2, it only has 1 hydrogen attached to it. Great. So learning bond line structure will simplify having to draw all this for a simple butane molecule when we could have been drawing just this the entire time. Great, so that's bond line structure. Now let's move on to substituents and carbon counting. Once we use bond line notation, we need a way to describe variation in structure. Let's start. 1, 2, 3, 4, 5. So this will be pentane because it has 5 carbons. But what if I add this right here? I just added an extra carbon. Great. Now how do I name this, right? Because now it's 6 carbons. Would it be hexane? Well, not quite. The way we do this is by identifying the longest parent chain. So the longest carbon chain that there is will be the parent chain. Let's locate that. We're going to start far away. 1, 2, 3, 4. And whichever way I take will be the longest parent chain. So you know what? I'll just take the normal way. 1, 2, 3, 4, 5. So the parent chain is 5 carbons. So as a result, it'll still be pentane. And since there's no double bond or triple bond, or there's no ring, it just stays as ane. Now, how do we deal with this right here? And what even is that? Well, that is called a substituent, which is an alkyl group that branches off the main carbon chain. Well, that's the fancy definition for it. But I just like to think of it as an extra carbon group or any extra atom that's just bonded to the main chain. Where the main chain is just the longest continuous carbon chain there is. For example, what is important is the naming part. Since we only added 1 carbon, that corresponds with the prefix meth, but it's not methane, right? Because since it's a substituent is called an alkyl group. So as a result, substituents are given the YL root, is it called? I'm not sure. This is an English class, but it is given that ending. So it'll be a methyl group. That we added to the parent chain right there. Now, when you name it, now that we know there's a methyl substituent added to the pentane carbon chain, how do we know? We don't really know where the methyl group's placed, right? So we can't just name it methyl pentane. Where specifically, on what carbon is the methyl group attached to? You always give the substituent you place, the lowest number of the parent chain. Let me demonstrate. So if we go left to right, we do 1, 2, 3, 4, 5. If we go right to left, you get 1, 2, 3, 4, 5. So you could argue that the substituent is placed on carbon 4 if we go right to left, or on carbon 2 if we go left to right. You will always choose the substituent with the lowest number. So you will always choose the numbering that gives the substituent the lowest number. So, great. Now we know that it's placed on carbon 2. And so the way you go about naming this is by writing 2 dash methyl pentane. Just like that. Great. And this is why it's so important for you guys to know methyl. It's important for you guys to know methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. You will use those every single day. How about we do another molecule? So again, 1, 2, 3, 4, 5 carbons, but now let's add substituents. Interesting. So I added 1 carbon right here, and then I added 2 carbons over here, because each vertex is a carbon. And remember, there's implicit hydrogens. So if this middle carbon right here has 1, 2, 3 bonds to other carbons, then that means it has to have 1 hydrogen attached to it. Great. Now, how do we go about naming this? Well, you have to find the longest parent chain first. I'm going to start over here. 1, 2, 3, 4, 5. However, if I do 1, 2, 3, 4, 5, that would also work. So you can truly choose either one. I'm just going to go with 1, 2, 3, 4, 5 with the middle one. So since the longest parent chain is 5, that means it will correspond to pent. And since there's no double bond, triple bond, or there's no ring, it will be the ane ending, since it's an alkane. Now there's 2 substituents, which is this one and this one. Remember, substituents end in IL because they're called alkyl groups. So as a result, since this one is 1 carbon that was added as a substituent, it will correspond to the prefix meth. And since it's a substituent, I will add YL, so it's a methyl group. The second substituent we added is 2 carbons, which will correspond to the prefix eth. And since it's a substituent, I will add the YL ending, ethyl group. Now, how do we know how to number them, right? So we will go 1, 2, 3, 4, 5. That's our parent chain identified. Remember, you want to give your substituents the lowest possible numbering. So I will go left to right. 1, 2, 3, 4, 5. And right to left of your main parent chain. 1, 2, 3, 4, 5. So if I go left to right, that will give my methyl group carbon 2, and that will give my ethyl group carbon 3. If I go right to left, that will give my ethyl group carbon 3 and my methyl group carbon 4. Clearly, left to right is a lower count numbering, so we will go left to right. So our ethyl group will be carbon 3, and our methyl group will be carbon 2. So it will be 2 methyl pentane excuse me, and then 3 ethyl. You might be asking yourself why I added it this way. Well, another rule that you should take note of is that whenever you have multiple substituents, you have to place them in order, not in numerical order. As you can see, I put the 3 before the 2, but it's actually in alphabetical order. So E comes before the M in the alphabet. As a result, the ethyl group must be placed first, before I place the methyl group in the main name of the molecule. So as a result, we have 3-ethyl 2-methyl pentane. This should tell you that the ethyl group is placed on the third carbon. Ethyl, having a YL ending, means it's a substituent. Eth prefix means it's 2 carbons. 2-methyl means methyl ending in YL is a substituent. Meth is a prefix for 1 carbon. The 2 means it's on carbon 2. And pentane means the main carbon chain is 5 carbons. And since it has an ane ending, that means it's an alkane. So there's no double bond, no triple bond, and there's no ring. Great. So yeah. Part 3 of what we have to cover will be structural isomerism. So structural isomers have the same molecular formula, but different connectivity of atoms. For example, let me write the definition clearly. Oh, here's a little thumbnail I drew. Let me bring this a little bit down so we have enough space to draw. So the clear definition for structural isomers or structural isomerism would be that they have the same chemical formula as we saw between propane and cyclopropane. Actually, no. Let me go up and let me make sure between what 2 molecules it was. Between propene and cyclopropane. Same formula, different structure. So, structural isomers have the same formula, different connections. So their atoms are arranged in different ways. For example, C4H10. A question could be asking you to draw all the possible structures, all the possible structures for this formula. You could submit it to a degrees of unsaturation test to determine if there's any rings or double bonds or triple bonds affecting the saturation of the compound. Or you could genuinely just go for it. So, we have 2 external carbons. Each external carbon always has 3 hydrogens. And we have 2 internal hydrogens, which each has 2 hydrogens. So that means in the internal carbons, there's 4 total hydrogens. External, there's 6. So that means there's 10 hydrogens in this structure right here, which matches up with butane. What's another structure you could draw, though? Well, since we only have 4 carbons, I'm gonna draw the main parent as a propane, and I'm going to add our 4th carbon as a substituent. Great. Now we have 4 carbons, and now let's verify our hydrogens. As you can see, we have 3 external carbons. So that means each of them has 3 hydrogens, and you can verify this by seeing that each of these carbons only has 1 bond to another carbon, meaning it has to be bonded to 3 hydrogens, as you can see. But that means this inner carbon will be bonded to 1 hydrogen. So if all the other 3 carbons are bonded to 3, that means they make up 9 hydrogens, and the inner one with just one makes up the 10th hydrogen, so this is also the same formula, just a different structure. So that's my method of doing isomers. I personally start off with the main chain, such as butane. Here we started with butane. And then I decrease the carbon by 1. Well, I decrease the main parent chain by 1 carbon, and then I just tried adding the extra carbons as substituents. However, I also perform a degrees of unsaturation test just to make sure. I can straight up recognize it's butane because of the formula CnH2n plus 2. If you do the math, it's the same. It's a saturated alkane, but if you were to submit it to this test, you would get 2 times 4 plus 2 minus 10 actual hydrogens present. We get 2 times 4 is 8 plus 10. 10 minus 10 is 0 over 2, so 0 degrees of unsaturation, meaning it's a fully saturated compound. So after that, you just kind of, again, the method I do for structural isomers. Draw main chain. Yeah. However, / perform degrees of unsaturation test. Because I recognized that this formula matched this, I did not instantly do a test because I knew it was already saturated. But if you can tell there's something weird, or if you're unsure, just do the test using the formula, and you'll be able to find if there's a ring or a double bond present, which will guide you on creating those structures. So otherwise, draw the main chain for your first structure, and then just decrease the main chain, the main carbon chain, by 1 carbon, and add extra carbon as a substituent. I honestly do this a lot, and I just keep, let's say it's like heptane, like 7 carbons. I just keep decreasing the carbons, and then I just keep adding more substituents, like an ethyl and a methyl, once I'm at like 4 carbons for my main carbon chain, so a butane. But that means I still have to add 3 carbons as substituents, so I try adding a combination of substituents at different parts of the molecule. It can get tricky, but it's all practice. Again, I'm going to publish videos where I go over practice problems and such, but this is just the theoretical information or background information you need. So yeah, I will not dwell on this too much. We already went over naming alkanes. So step-by-step method, I will repeat it. You can take notes. You find the longest continuous carbon chain, as this will determine the parent alkane. Then you number the chain to give the substituents the lowest possible numbers. You name and locate substituents, such as methyl, ethyl, propyl, etc. And you assemble the name. Number dash substituent dash parent alkane. An example. Now, I actually want to do one example before I finish the video. Actually, no. We have to move on to naming cycloalkanes. I forgot to go over that. If you want to name a cycloalkane, it's pretty simple, honestly. We have ourselves a little cyclohexane molecule here because it has 6 carbons. If I were to add a methyl substituent here and an ethyl substituent here, I would just start. It doesn't matter where you start on this cycloalkane because it's a ring system, right? It's closed. You just always want to start at either one of your substituents. And you want to count in a way that gives your substituents the lowest number possible. So 1, 2, 3, 4, 5, 6. No matter what way I go here, it will always give the lowest number, but you want to test that with the specific cycloalkane you have. So for methyl, we have it on the first carbon, and for our ethyl group, we have it on our second carbon. So this will be 2-ethyl. Remember, alphabetical order when you're placing your substituents, not numerical. Then 1-methyl, and it's just a cyclohexane. Ane because it's just single bonds. And that's all you have to know about cyclo. Cycloalkanes are just named the same way, except the parent chain is a ring. So you have to identify the ring as the main carbon chain. Always, okay? Even if your substituent is like a heptane, your ring is always your main parent chain. So, in this lesson, we learned how organic chemists see molecules through bond-line notation that simplifies structures, isomerism, which explains diversity, and blends our knowledge of saturation, and naming rules that let us communicate clearly and finally know and understand how to name alkanes, understand their structures, and understand saturation. In the next lesson, we'll begin introducing pi bonds and alkenes, where structure starts directing reactivity. Thank you.